Hi and welcome. In this video segment, I want to talk about another model for understanding the structure and function of atoms. And I'm going to focus on atoms and how they form anions and cations. Now, this leads us into bonding. And when we get into bonding, we're really only interested in our valence electrons. Those are the ones that are involved in bonding. So this is a model that will bridge the structure of the atom to structure of ionic compounds and covalent molecules. So that's what my intent is here. Now, to get your valence electrons are your outer S and P. But we find that the group number is helpful in getting us our valence electrons. Group number 1 has 1. Group number 2 has 2. I don't think that valence electrons are meaningful personally for transition elements. So let's hop over to the representative P. Group 13 has 3. It's S2P1. Group 14 has 4. Group 15 has 5. 16 has 6. 17 has 7. 18 has 8. Hopefully you see that pattern. So what we're going to do for the Lewis dot structure is only show those valence electrons. So if I have strontium, what we're going to do, and I don't want you to draw this, but I want you to envision a square around the element symbol. We don't draw the square, you simply envision the square. Strontium has 2 valence electrons. It has 38 electrons, but only 2 of them are going to be involved in bonding. I personally don't care whether you start left, top, right, bottom. Some teachers and professors do, so you need to listen carefully in class. So strontium, I'm going to follow Hund's rule, and I'm going to put them in unpaired before I pair them up. So strontium without the square that I have drawn would look like this. Okay, now strontium is a metal, and metals are losers in the electron game, and so they're going to lose electrons to form cations. So strontium is going to lose those 2 electrons. So it's going to have no dots around it because it lost those 2 electrons. So how do I distinguish this as a Lewis dot structure? Well, you put brackets and the charge just outside the bracket. So this would be the Lewis dot structure of the atom. This would be the Lewis dot structure of the ion. And I don't know if you've ever had it, but I love IBC root beer. It's a really good root beer. And so I remember that acronym that if it's ions, make sure I use brackets and charges. Okay, so I want to do a few more of these just to make sure we have this down. Let's take a look at aluminum. So aluminum has 3 valence electrons, and I put them in unpaired before I pair them. When aluminum becomes an ion, it loses those 3 valence electrons. So I have to put brackets and a charge. No more dots because it's lost all those dots. Okay, so it forms the aluminum cation, Ca positive ion, right? A cation. All right, now I want to do a trickier metal. I want us to do bismuth. Now, bismuth, here's why bismuth is tricky. Because bismuth has 5 valence electrons, right? It's in group 15. It has 2 S's and it has 3 P's. So I'm going to go 1, 2, 3, 4. Once you get around, now we're going to pair it up. Now, why bismuth is tricky is bismuth can form two ions. So in the first one, it will lose those 3p electrons. There's 6p, but there are 3 of them. So it's going to lose, let me write it this way so I think it'll be much clearer, I hope. It's the 6p3 electrons. Okay, when it does that, it had 5, it lost 3, so I am going to draw 2 electrons and put a 3 plus charge. Now, it can also lose the 6p3s and the 6s2s. So if it lost 5 electrons, it had 5 dots representing 5 valence electrons. Now it has none, and it has a 5 plus charge. Okay, now how would you know which to draw? Well, the question should tell you. And that's why, and this gives you a glimpse of naming, we would have bismuth 3, and then we would have the other part of the name, because we have to distinguish bismuth 3 from bismuth 5. Okay, and so somehow the question has to communicate to you. Now let's do a couple of anions. Let's start with phosphorus. Phosphorus is in group 15. It has 5 valence electrons. So phosphorus ends in 3s2, 3p3. So it has 5, 1, 2, 3, 4, 5 valence electrons. Notice I went around the square and I didn't pair up until I had to. Now, nonmetals are winners to become an anion, a negative ion. And it's going to become just like the next noble gas. And so it's going to gain 3 electrons. So if I had my phosphorus that I had before, it'll gain 3 electrons from what? Well, probably a metal, and to the metal ion. So you add 1, 2, 3. It had 5, it now has 8. You want to represent those full 8 electrons, but don't forget ions, brackets, charges. Okay, what if we did bromine? So bromine, oh, by the way, this is important. Anions change their name. So this would be now called the phosphide anion, or the phosphide ion. Okay, so if I have bromine, bromine's in group 17. It has 7 valence electrons. 1, 2, 3, 4. Don't pair till you have to. So that is the bromine. It can gain 1 electron to be just like the next noble gas. So I'd have bromine. This is what it looked like before. If it gains 1 electron, now it has a stable octet. Not everything obeys this octet rule, but that tends to be stable. So when we had strontium, it lost 2 to be like the previous noble gas. Nonmetals gain to be like the next noble gas. Don't forget ions, brackets, charges. Now, only anions, cations don't change their name other than saying strontium ion as opposed to just strontium. This would change its name to become the bromide, instead of bromine, bromide ion. Okay, so this is a great model, and it's going to be a nice bridge to when we get into bonding, from atom to ion to bond. Thanks for watching.